Hello, this is Steve Regan of the Modeling of Watershed Systems group. This presentation describes the surface runoff modules, S-runoff sea area and S-runoff SMIDX. This cartoon illustrates flow paths in the hydrologic cycle. The yellow lines represent flows computed by the surface runoff modules. The flows are Hortonian surface runoff, soil infiltration, impervious storage processes, and optionally cascading Hortonian flow and surface depression storage processes. The cascading flow and surface depression storage options are described in other training videos. Hortonian surface runoff computed from impervious, pervious, and surface depression fractions can flow directly to the stream network and cascade from HRU to HRU. Infiltrated water flows into the soil zone storage and/or as direct recharge to groundwater storage. This cartoon illustrates the hydrologic cycle from the PRMS worldview. The dashed lines are internal fluxes, and the solid lines are fluxes leaving or flowing to an HRU. Precipitation, air temperature, and solar radiation drive the storage and exchange of water in and from each water storage reservoir. The primary reservoirs are the plant canopy, snowpack, impervious surfaces, surface depressions, soil zone, and groundwater storage. Surface depression storage is not shown. It is similar in conceptualization to impervious surfaces in that it occupies a fraction of the HRU land surface area and has a specified maximum water holding capacity. The pervious fraction of the HRU is 1 minus the fraction of impervious area minus the fraction of surface depression storage area. Inflows to the surface runoff modules are rain throughfall as computed in the interception module, snowmelt as computed in the snow module, and potential ET as computed by the selected potential ET modules. Optional inflows to HRUs as computed in the surface runoff modules are cascading Hortonian surface runoff and capture of a specified fraction of Hortonian surface runoff in surface depressions. Outflows are Hortonian surface runoff from the pervious and impervious fractions, soil infiltration to the pervious fraction, evaporation from the impervious and surface depression fractions, and spillage, interflow, and seepage from the surface depression fraction. PRMS has 4 types of HRUs: inactive, lake, land, and swale. The surface runoff modules have no computations for inactive and lake HRUs. All processes are computed for land HRUs. Lateral flows are not computed for swale HRUs. Thus, computations related to Hortonian runoff, except for surface depression runoff capture within an HRU, are not computed, while all other land HRU processes are computed. This slide gives an idealized estimate of the partitioning of rainfall into surface runoff and soil infiltration. The remaining fraction is attributed to ET, 40% for the natural area and 30% for the urban area. Urban areas can produce significant stormwater flows as much of the runoff is routed directly to the stream network. In this example, the urban area has 45% more runoff and 35% less infiltration than the natural area. To mitigate the impact of impervious surfaces in new urban and suburban development, detention ponds are constructed to reduce surface runoff and increase infiltration. This slide illustrates the impact of impervious surfaces on peak stormwater flow. The baseline condition is 100% forested. Scenario 1 is 25% developed, Scenario 2 50%, Scenario 3 75%, and Scenario 4 100%. As development increases, peak stormwater discharge increases. However, the increase in stormwater flow may be nonlinear. Part of the nonlinearity is related to reduced soil infiltration and plant transpiration as development increases. Users could develop simulations using different values of impervious fractions to estimate changes in stormwater flow. This figure shows 5 types of lateral flow processes. The top 2 graphs are conceptualizations of infiltration excess, which is termed Hortonian runoff. The first represents stormwater flowing across the entire land surface with some infiltration, such as over soil with low permeability. Computation of Hortonian runoff from impervious areas is based on this conceptualization. The second graph illustrates stormwater infiltrating upslope, with some water infiltrating and some flowing as Hortonian runoff near the bottom of the hill slope. This is a partial contributing area process and is used to compute Hortonian runoff on pervious areas. The third graph illustrates saturation excess Hortonian runoff, where upslope stormwater infiltrates and near the bottom of the hill slope water is discharging to the land surface. The fourth curve illustrates subsurface storm flow, where water infiltrates to areas where the water can flow quickly through high conductivity features such as animal burrows, root channels, leaf litter, gravel layers, etc. This type of flow is termed preferential flow in PRMS. The fifth curve illustrates water that has infiltrated the soil and moves laterally downslope based on soil characteristics and gravity. This type of flow is termed interflow in PRMS. Dunnian, preferential flow, and interflow are computed in the soil zone module that is described in another training video. This slide illustrates the partial contributing area process. The cyan areas are where infiltration and/or saturation excess are occurring. The yellow areas are where the soils are below their water holding capacities. This slide illustrates the expansion and contraction of contributing areas. As soil saturation expands during a storm, the contributing areas expand. As the soils dry as a result of ET, recharge, and lateral flows, the contributing areas recede. The amount of water available for Hortonian runoff, infiltration, and surface depression storage processes are rain through fall, snowmelt, and cascading Hortonian runoff. A portion of snowmelt can be specified to be the first component of infiltration and thus not available for computation of Hortonian runoff. The photograph shows water flowing on the land surface due to infiltration excess. Hortonian runoff for the pervious fraction is computed using one of two partial contributing area algorithms. The S-runoff C area module uses a linear algorithm, and the S-runoff SMIDX module uses a nonlinear algorithm. Both algorithms take into account the antecedent soil water storage. The S-runoff C area module uses the fraction of water content in the recharge zone of the capillary reservoir, while the S-runoff SMIDX module uses the total water content in the capillary reservoir. Users select one of the modules using parameter S-runoff module that is specified in the control file. The algorithms compute contributing area based on parameters that are specified in the parameter file. Parameters are shown in bold font and described on the next slide. Hortonian runoff is computed as the contributing area times the available water. This slide shows the primary parameters that control pervious Hortonian runoff and impervious computations. The parameter C area max, the maximum contributing area, can be the most sensitive parameter to compute peak flows. The pervious runoff parameters C area min, SMIDX COF, and SMIDX EXP are very sensitive for the flashiness of stream flow, while the soil parameters soil moist max and soil recharge max are sensitive for the full range of stream flow. The impervious parameters, HRU percent imperv and imperv store max, are very sensitive for peak flows and the flashiness of stream flow. If the simulated stream flow is much flashier than observed, it may be necessary to reduce the impervious fraction. If the simulated ET is higher than expected, it could be that the specified impervious fraction and/or impervious water holding capacity are too large, as water on impervious surfaces evaporate at the potential ET rate. A great deal of attention and analysis may be needed to estimate impervious parameter values. Parking lots, roads, sidewalks, and building roofs can direct stormwater directly to the stream network via storm drains, gullies, and ditches. However, in some cases, this runoff may be directed to detention ponds that are used to promote soil infiltration and recharge. Runoff from some roads, driveways, sidewalks, patios, and roofs may drain to adjacent grassy or forested areas and infiltrate instead of flowing directly to the stream network. Additionally, stormwater on compacted soils and rock outcrops may drain directly to the stream network and/or infiltrate. There are many factors to determine the fraction and water holding capacities of impervious areas that is effective. This slide shows the primary parameters that control surface depression computations. There are several other parameters listed at the bottom of the table that generally are less sensitive than the ones defined. The most sensitive parameter is the surface depression storage fraction, DPRST-FRAC. This slide shows components for soil infiltration computations. The amount of infiltration is the sum of throughfall, cascading Hortonian runoff, and a portion of snowmelt minus pervious Hortonian runoff minus direct recharge. Infiltration is limited by the unsatisfied capillary reservoir storage and is for the pervious fraction. This slide shows components for the impervious fraction computation. The amount of impervious Hortonian runoff is the antecedent storage plus the maximum available water minus the maximum storage capacity specified by parameter ImpervStorMax. Evaporation is limited by the fraction of each area that is snow-free. Water evaporates at the potential ET rate and is limited to the amount of unsatisfied potential ET, which equals the potential ET minus evaporation from the canopy and sublimation from the snowpack. See the PRMS 4 manual for a more detailed explanation of the surface runoff modules, which can be downloaded from this webpage. Be sure to download the changes in the specification of user inputs document, which provides updated tables. Table 2 contains descriptions of available modules. Table 1-2 contains descriptions to the parameters that can be specified in the control file. Table 1-3 contains descriptions of the parameters that can be specified in the parameter file. Table 1-5 contains descriptions of all variables that can be written to the various output files. The FAQ tab can be very helpful as it provides common questions with answers that users have submitted to the Mose group over the years. If you have questions about the surface runoff module or need help for other issues related to PRMS, you can click on the Help tab and fill out the contact form.